Hello everyone, this video covers sections 11.9 and 11.10. 11.9 is called representation of function or functions as power series. Now just to refresh your memory, recall that a power series looks like this. If it is represented around A, and if A is equals to 0, it's going to actually be called a Maclaurin series, but we'll talk about that in the next section. So the examples we did before, it was something like this: x to the n, or n factorial, n equals to 0 to infinity, and so forth. And what we did before, we found two things. We find the interval of convergence and the radius of convergence. So that's what we did before. So now, in this section, we're going to use power series to represent basic functions that we have before. So we're going to start with the most basic power series. So if you look closely, this is technically the geometric series. Okay. And remember that the geometric series is convergent only if the absolute value of x is less than 1, and the sum is equals to this. Okay. Now in this section, you're going to learn how to use a series representation like this one, to create series representation of other functions. And in 11.10, you'll see how we get these functions. Like, how do we know that this is equals to this? Okay. But these functions are very, very interesting for this reason. Look, we already know that the power representation from 1 over x is equals to this. So this is going to be like the basis for many things we want to do. So, for example, let's say that you wanted to know, and this is technically just basic algebra substitution, that you wanted to know what is the power representation of 1 plus x. So, very simple. Okay. So what's the relationship between this one and this one? Remember, this will be the basis that we're gonna come to. Well, notice that this is the same thing as 1 over 1 minus x. So minus and minus will give you the plus. And now you can use the basis function, which is this one. So therefore this will be 1 and then plus minus x squared minus x cubed and so forth. Now if you write this in series notation, it will be the sum from 0 to infinity minus x to the n. So you just substitute the x by minus x, and then this you can rewrite like this: 2n equals to 0 to infinity Now, using the same basis function in the example we just created, so we know that this is equals to this. One of the good things about power series is that it makes some functions that could be hard to integrate or differentiate, at least you can now do something about it. Now, don't forget that this is the same thing as if n is equals to 0, then this is equals to 1, which we have it here. So remember that this is the same thing as 1 minus x plus x squared minus x cubed plus x to the 4 minus x to the 5th and so forth. Okay. So now let's say that we integrate both sides. So you integrate 1 over 1 plus x dx, so that's the left side. Notice that you should be able to integrate here 1 by 1. And this is the reason why power series are very powerful and useful, especially in higher math classes. If you're gonna study applied math, power series are an essential part of this. So remember, the integral of this is equals to ln of 1 plus x. And here you can integrate 1 by 1. So this will be x, this will be minus x squared over 2 plus x cubed over 3, and so forth. Okay. Now you have to write this in sigma notation or summation notation. So remember, this has to equals to the sum, and you just have to be careful with the starting point. So this one starts in 0. In theory, you can also make this one start in 0. You just have to make sure that this actually works. Notice that the first one is positive and then negative. So therefore, we're going to need minus 1 to some power, and it could be n plus 1 or n minus 1. If n is 1, notice that 1 minus 1 is 0. Anything to the 0 power is 1, so it will be positive. Then times x to the n. If n is 1, this will be 1. If n is 2, you'll get 2, and so forth. And then on the bottom, this will be n. And obviously, this goes all the way to infinity. So therefore, the power series representation for ln of 1 plus x is equals to this. And notice how it was very easy to get this. Everything came just from the basic we were using right here. So we technically get 2 formulas already. We're going to get more right now just from here. So this is the basis. A small substitution, you get this. You can integrate both sides. You can actually also differentiate both sides, and so forth. Okay. Now, just for the record, notice from here you could integrate straight without doing the expansion. I highly recommend at the beginning to expand things like this so you can convince yourself that this is equals to this. Otherwise, so notice you could integrate this, and the integral of x to the n, remember, is x to the n plus 1 over n plus 1. And these are almost identical, but once you change the starting point, that's why the n plus 1 is going to go down to n. So in theory, this is correct, and you start with 0 here, okay? But it's easier for you to visually see if you write out the terms so you can visually see what's going on. All right, so let's do one more example using this same formula. And let's say that we want to find out the power representations of 1 over 1 plus x squared. Remember, you had to write it using this format, so notice that this is the same thing as this 1 over 1 minus x squared. Okay. So therefore, if we use the formula or the summation, it's going to be the sum from n equals to 0 to infinity of minus x squared to the n, which we already say you can rewrite this as n equals to 0 to infinity minus 1 to the n, and this will be x to the 2n. Hence, this is the power series representation in this function. But let's go one step further, and let's say that we again integrate both sides. So if we integrate both sides, this is a integral that we have done literally 1,000 times. Okay. And if we integrate both sides, this will be the same thing as the integral of the sum. And again, if it may be easier if you expand this. Remember, if this is 0, obviously anything to 0 is 1, then it will be minus x squared, and then plus x to the 4, and so forth. So if we integrate this will be the sum from n equals to 0 to infinity, minus 1 to the n. It will be x to the 2n plus 1 over 2n plus 1. But this one, remember, is tangent inverse. So therefore, from here you can get the power series representation of tangent inverse. So tangent inverse is the same thing as this. Now you will see in the next section that if you want to do this from scratch, which I'm going to show you how to do this from scratch, it will take you a long time to get this formula. While using this, it's very easy to get to the formula. Now I highly suggest you start memorizing these formulas because you're going to use it over and over. So this is the power series representation of this one, and you should definitely memorize this because everything we done so far came from this one. Now this power series representation also has a huge advantage, especially when you're going to use numerical methods, which are used in engineering, and that's mostly how you actually calculate integrals. So you may have an integral that is a little tricky to find, but with using power series, you can approximate it pretty easily. So for example, let's say you have the following function: f of x is equals to 1 over x squared times tangent inverse of x. And you want to integrate this. Well, the integral may be a little tricky to do. Not impossible, but a little tricky. But this is what we want to do. So we already know that this part, you can represent it as this. Okay, so we already know that f of x, you can rewrite it as tangent inverse, which is this much. Okay, minus 1 to the n over 2n plus 1. Okay, so you already know that. Now, if you multiply by 1 over x, which notice this is the same thing as x to the negative 2, it will be like multiplying this by x to the negative 2. And recall from basic algebra that you have x to the a times x to the b. Well, this is just x to the a plus b. Notice that the summation is with respect to n, not with respect to x. So you can put this inside and simplify, and this will give you the summation from n equals to 0 to infinity minus 1 to the n. It will be x to the 2n minus 1. How do we get that? Well, 1 minus 2, using this rule, is minus 1. Everything divided by 2n plus 1. So therefore, from here we can find that the integral of f of x dx is just the sum of the integrals from here, and as you can see, they should be very easy to integrate. So this will be the summation from n equals to 0 to infinity minus 1 to the n times 1 over 2n plus 1. Then the integral of this is going to be x to the 2n. Remember, you have 2n minus 1 plus 1. So give you 2n. And then there is a constant where you may have to adjust this. But now this will be the power representation of this integral, so that means you can use this to integrate this or to approximate this. Okay, so now let's look to the power series representation of sine of x. And in the next section, I will tell you how they come up with these formulas. For now, just take it as a given, the sine of x is equals to this. And I highly recommend you to memorize these formulas. Also, it's very important for visual purposes to see this in actual expansion form. So notice that we want to start with n equals to 0. So if n is 0, the first value will be 2 times 0 plus 1, which is just 1. Anything to the 0 power is 1. So therefore, the first value will be just x. Then if n is equals to 1, it will be 2 plus 1. 2 times 1 plus 1, which is 3. So then it will be minus x cubed over 3 factorial. Then the next one will be x to the 5th over 5th factorial minus x to the 7 over 7 factorial, and so forth. All right, so now using this series, either this one or this one, we're going to use it to find the power series representation of other series related to sine of x. For example, let's say we wanted to find the power series representation of f of x equals to sine of x squared. All right, so if we use this formula, the sine of x equals to this, and obviously therefore equals to this, let's see what we got. So therefore sine of x squared, so now we're gonna just replace x for x squared. This will be x squared minus x squared cubed or 3 factorial plus x squared to the 5th over 5 factorial, and so forth. X squared to the 7 over 7 factorial, and just keeps going forever. Therefore, if we write this in sigma notation, this will be the sum from n equals to 0 to infinity minus 1 to the n, because it keeps changing from positive to negative, so it's alternating. But notice that this will be now x to the 6, x to the 10. So relating that to the starting point, this will be the same thing as doing this. So notice that you have x squared to the 2n plus 1. It will be x to the 4n plus 2. So therefore, this is going to be to the 4n plus 2. The bottom is still going to be 2n plus 1 factorial. Now, just to verify that this is correct, let's check a couple of them. If n is 0, notice the 4 times 0 is 0 plus 2 is 2, which is the 2 right here. 2 times 0 is 0 plus 1 is 1, so 1 factorial is 1. Now, if n is 1, then this will be 4 times 1 is 4 plus 2 is 6, which you'll get the 6 from here. And the bottom is still 3 factorial. So clearly this is the correct answer. So therefore, if I ask you what is the power series representation of sine squared, then this is what it is. That's it. It is that easy. All right, let's try another example. Let's go back to the original function. Remember, sine of x is equals to this. And you should be able to know that this and the summation thing is the same thing. So now let's see what happens when you take the derivative with respect to x in both sides. Okay. So what's the derivative of x? Obviously is 1. Now notice the 3 factorial is the same thing as 3 times 2 times 1. This one obviously is 5 times 4 times 3 times 2 times 1, and so forth. Okay. So there should be no mystery. So the derivative of x is 1. Now the derivative of x cubed is going to be minus 3. But notice it will be 3x squared. The 3 will cancel. So it will be x squared over 2 times 1. The next one, notice that the derivative of this is 5x to the 4. So the 5 will cancel. So it will be x to the 4 over 4 times 3 times 2 times 1. And it should be obvious that the next one will be x to the 6 over 6, 5, 4, 3, 2, 1. So notice that this is the same thing as just 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial, and so 4. So this keeps going. X to the 6 over 6 factorial. But the derivative of sine is cosine. So therefore that implies the power series representation for cosine should be this. Now I will write this in sigma notation. This is the sum from n equals to 0 to infinity, negative 1 to the n, and then it's x to the 2n over 2n factorial. Which, if you look closely to this, it should be obvious that if you take the derivative of this, it will give you this. So this is not a secret. And now that we have the power series for cosine, which we got from sine, then you can also use that to come out with different series for other functions and integrate or differentiate functions. So for example, let's say you want to find the power series representation of x to the a cosine 3x. So now we should be able to find cosine 3x pretty easily using the function. So this is what I mean. So cosine of 3x using this function should be the sum from n equals to 0 to infinity, negative 1 to the n, and then it will be 3x to the 2n divided by 2n factorial, which is the sum from n equals to 0 to infinity, negative 1 to the n. Then it will be 3 to the 2n, and then x to the 2n divided by 2n factorial. Notice how this looks more like the power series that we did in 11.8, where they ask you to find the radius and integral your convergence. So therefore, if you multiply this by x to the a, all you have to do is add that to the x value. So therefore, this should be the sum from n equals to 0 to infinity, negative 1 to the n, 3 to the 2n, x to the 2n times x to the 8, everything divided by 2n factorial. Then if you simplify this, it will be the sum from n equals to 0 to infinity, negative 1 to the n, x to the 2n plus 8, and everything divided by 2n factorial. Now, once you have this, it could also be very easy to integrate this by integrating both sides. And if we do that pretty quickly, let's say that, so we have more space here. So therefore, the integral of x to the a cosine 3x, and you should check this, it's going to be the sum from n equals to 0 to infinity, minus 1 to the n, 3 to the 2n, and then it will be x to the 2n plus a plus 1, which will give you 9, divided by the 2n factorial that you already have there, times 2n plus 9. And that's it. That's how easy it will be to find the integral of this. All right, so now let's go to section 11.9, and this section is the one used to come out with the formulas we use in the previous section. This is actually 11.10, not 11.9. So we have the following theorem, which is what is driving everything. If f has a power series representation at a, sometimes this is called expansion. That is, if f of x can be written like this, where this is the part that is new right now. To find these values, this is the n derivative evaluated at a divided by n factorial. Okay. Now, if we expand this, and this is one of the most useful things in the whole class, the following, this will be z0 x minus a to the 0 power, which is just z0 plus c1, and so forth. c2 x minus a squared, and it keeps going. Now, so note, if a is equals to 0, then the Taylor series is called Maclaurin series. I think I spelled it wrong. Okay, Maclaurin series, which is the most commonly used. So So the generic name is Taylor, and if A is 0, it's called a Maclaurin series. All right, so let's find the Taylor series, or in this case, the Maclaurin series for this function. Okay. So this is how, again, this is how they got the function that we have for sine and cosine before. This is what I mean. So far, in section 11.9, we have these functions, which I told you should just memorize. This is equals to the sum from x to the n. We also have sine of x. And there was a -1 to the n in the front. Infinity. And we also did the one for cosine. We also come out the one for ln, 1 plus x. And also the one from tangent inverse. Remember that these give you this, and sine give us this. Okay. Now the question, like, how did they get these two to begin with? So this is gonna tell us how they did it, which is technically this formula, which is technically the easiest example, but anyways, here it is. So we start with the function. So f evaluated at 0 is e to the 0, which is 1. Okay, so that's fine. So then what is f prime? F prime is equals to e to the x. And how much is f prime of 0? Is 1. So the reason why this is very easy is because the derivative is always going to be the same. F double prime of 0 is 1, and so forth. So you can see that the end derivative, which this is the hard part to figure out, is this, and obviously the end derivative evaluated at 0 is equals to 1. Okay? So according to this, well, Cn is going to be the end derivative, which remember is 1 divided by n factorial. So therefore, e to the x is going to be the sum from n equals to 0 to infinity of Cn x minus a to the n power. But remember, in our case, remember a is equals to 0. So it will be n equals to 0 to infinity of 1 over n factorial times x minus 0 to the n, which will be the sum from n equals to 0 to infinity of x to the n over n factorial. And this is the easiest one, but this is how they come out with this formula and this formula right here. And just like we did in the previous section, let's say that now we want to find the power series representation for this. Well, then f of x is going to be equals to the sum from n equals to 0 to infinity. But instead of x, you're going to put x squared. So then this will be x squared to the n over n factorial, which will be the sum from n equals to 0 to infinity of x to the 2n over n factorial. And that's how easy it is. So once you have a Maclaurin series or Taylor series for a specific function, there's no need to go through the whole process again. So if I ask you to find the Taylor series of this around some value, you already have a function like this, then it's all you have to do is just substitute in the original function, which in this case will be this one, and that's it. Now, also, just like the previous section, remember that if I ask you to do this before, okay, so this is a specific example. Remember that this is impossible to integrate because it's not an elementary function, but with Taylor series, you can do it. So this will be the sum from n equals to 0 to infinity, or the integral of x to the 2n over n factorial. So this will be the sum from n equals to 0 to infinity of 1 over n factorial, and then it will be x to the 2n plus 1 over 2n plus 1. And now you are able to, at the very least, approximate this integral, when in this form it's impossible to figure what this is. Now, if the function is not a Maclaurin series, then you have to be a little more careful, because this is going to change the function, and that would make things more difficult, a little bit more, or more work intense. So you have to be sure that you're using Maclaurin series when you're doing substitution, or that you are expanding it in the same value. So, for example, here we already know that the derivatives, the n derivative, is equals to e to the x from the past, but now if you evaluate the n derivative at 4, it's not gonna be 1 anymore. It will be e to the 4. So therefore, the n derivative, the Cn, which remember is the n derivative evaluated at a divided by n factorial, is going to be e to the 4 times 1 over n factorial. So therefore, f of x is going to be now the sum for n equals to 0 to infinity of e to the 4 over n factorial times x minus 4 to the n power. So contrast that with the function for e to the x, or the expansion for e to the x, which was 0 to infinity of x to the n over n factorial when a was equals to 0. So you can see that in here. This will be gone, will be x to the n over n factorial, and this will be 1. Now, one thing that you have to be very careful to distinguish is the difference between a Taylor series, which is what we did so far, compared with a Taylor polynomial of degree n. Remember that a Taylor series keeps going, it's going forever, where a polynomial is a finite thing. So going back to e to the x, remember e to the x was equals to 1 plus x squared over 2 factorial plus x cubed over 3 factorial to the 4 over 4 factorial, and so forth. So this is the series, because this is the sum from n equals to 0 to infinity of x to the n over n factorial. So therefore, this is a Taylor or Maclaurin series. But if you were going to stop, for example, here, so then this will be called the first polynomial, which is a linear equation. You were going to stop here, then it will be the second polynomial, and the degree will be obviously of second degree. And so for if we use this 3, then it will be the third polynomial, which will be 1 plus x squared over 2. And obviously, the more you use, the more terms you use, the more accurate it will be. Why is this important? Well, because you need to approximate things. So in reality, you will use the polynomials, not the series, because you will never going to go to infinity. So in general, for any function that has a Taylor series representation, you're going to have f of x. It will be a Taylor polynomial plus some remainder. And the remainder is going to be whatever is left. Like if you stop here, all of this will be Rn. If you stop here, all of this is Rn, and so forth. So notice that Rn is technically the next derivative or the next term. So you step here, it will be the following, and so forth. So you can think of this as, this is an approximation, and you can think like this is the error, but it's called the remainder, with the property that the limit as n goes to infinity of Rn of x is equals to 0, okay? Which Makes sense, because as you go to infinity, this keeps getting smaller, smaller, smaller. Now, like I say, the remainder is supposed to go to 0. And from there we get the follower called Taylor's inequality, which says the following, that the remainder always has to be less than or equals to m divided by n plus 1 factorial x minus a to the n plus 1, where m, okay, where the n derivative plus 1, which is what I just told you, has to be the next derivative evaluated at some point, has to be less than or equals to m. So technically the n plus 1 derivative has to be bounded, which is the case. And you look at this. This is what I was telling you. You go to this, you have to look to the next value, which this one came from the n plus 1 derivative. So if this is n, this will be n plus 1. If this is n, this will be n plus 1, and so forth. So this is the bound telling you what is the biggest error you can make. All right, so now let's do a function from scratch to get the actual Taylor series. And this is not that complicated, but it takes a little more work, and you have to be very careful to expand everything so you can see the pattern, because you need to get a pattern. Remember, at the end of the day, we want to find this cnx, in our case, plus 3 to the n equals to 0 to infinity, where cn is going to be the n derivative evaluated at minus 3 or n factorial. So this is what we want, and this is going to be the hard part to figure this out. So just do exactly the way I'm going to do it here. So here it is. So you have f prime of x. Remember, this is the same thing as just x to the negative 1. So it will be negative 1 is x to the negative 2. So therefore from here, f prime of negative 3, it will be negative 1 times negative 3 to the negative 2, or negative 1 over negative 3 squared. Okay. Again, don't simplify. Then let's go to the next one, f double prime, going to be minus 1 times minus 2 x to the negative 3. So this means that f double prime of negative 3, it will be negative 1 times negative 2 over negative 3 q. Okay. And you usually have to do at least 3 or 4 before you can see the pattern. F triple prime will be minus 1, minus 2, minus 3, x to the negative 4, and from here the third derivative evaluated at minus 3, minus 1, minus 2, minus 3, divided by negative 3 to the 4th power. All right, so by now it should be obvious that, the derivative, the first one is negative from here, then the next one will be positive. I'm talking about the top only. Then negative. So it's clearly changing from negative to positive. And you can always adjust the sign. So that means that the n derivative evaluated at minus 3 is clearly going to be minus 1 to the n or n plus 1 or n minus 1. We can always adjust that. But notice that if this is 3 derivatives, this is 1 times 2 times 3. If it was 2, this is 1 times 2, and so forth. So therefore, this is 1 times 2 times 3 all the way to n. Then on the bottom, this will be minus 3. Notice that this is 1 more than this. This is 1 more than this. So this will be 3 to the n plus 1. So you can rewrite also the top as n factorial. So this will be minus 1 to the n factorial divided by minus 3 to the n plus 1. Okay. Which you can also write minus 3 to the n plus 1 as negative 1 times 3 to the n plus 1. So it will be minus 1 to the n plus 1. And then 3 to the n plus 1. You want to. Okay. But let's leave it like this for now. So therefore, you can say that f of x is going to be equals to, remember the sum from n equals to 0 to infinity of Cn x minus a, which will be plus 3 to the n, where Cn is going to be the n derivative evaluated at n, which is this part. Remember this. So we're going to need, so that's going to be minus 1 to the n factorial divided by n factorial. So then factorials will cancel. And then times x plus 3 to the n. Okay. So therefore this is the sum minus 1 to the n x plus 3 to the n over minus 3 to the n plus 1. And again, you can simplify this more, but for now this is okay. So as you can see, to get things from scratch is a lot more work. So that's why if you already have a power series representation for something, you should just use it. Otherwise, to do it using this method is going to take a long time. So this will be the answer. Now again, the key to get this is to not simplify this in the beginning, otherwise you will not see the pattern. Now, in the other hand, if you were trying to find the Taylor polynomial, which you only need the first two derivatives, then it will make sense to simplify. For example, this is equals to minus 1 over 9. This one, it will be 2 over, or minus 2 over 27. Okay? So therefore, you want to find t2 of x, which is the second polynomial. Then it will be the first, only the first two terms, and you will use these two values. So you need the first one there, and then it will be minus 1, 9. It will be x plus 3 for the first derivative. Then minus 2 over 27, x plus 3 squared for the second derivative. And then remember, the zero derivative is just the function evaluated at the initial point. So this will be 1 over minus 3. So this will be the second polynomial. For this, it makes sense to simplify the derivatives as soon as you find it, but if you're trying to find this, simplifying like this is not gonna help you. It's actually, you will not be able to see the pattern. So if the question is to do this, you should definitely do it this way. All right, so let's do one last example. Here we also have a Maclaurin series, so f prime is going to be k 1 plus x to the k minus 1, and obviously f prime of 0 is going to be k times 1 plus 0 to the k minus 1, which is just k. Then f double prime is going to be k times k minus 1, 1 plus x to the k minus 2. So obviously f double prime of 0 is going to be k times k minus 1. And hence triple prime obviously going to be k minus 1, k minus 2, 1 plus x to the k minus 3. And you can see this is not hard, it just takes a while to write the whole thing. Just be careful when you write everything down. So clearly from here, by the way, they have this same example in the book, so you want to compare the solutions. So the n derivative obviously is going to be k minus 1, k minus 2. So notice the relationship between this one. So the 2, this is 3, this is 2, this is 2, this is 1, this is 1, and this is 0. So that's going to be very important. So therefore it's going to be times k minus n plus 1, then 1 plus x to the k minus n. And obviously when you plug in the value for 0, this is just going to be k times k minus 1, k minus 2, all the way to k minus n plus 1. Which again, the k minus 1 should make sense because see, if n is 3, this is a k minus 3 plus 1. So therefore, f of x is going to be the sum from n equals to 0 to infinity of the n derivative, which is this k minus 1, all the way to k minus n plus 1, divided by n factorial, and then this will be x minus 0 to the n. This has a special name. This is actually called a binomial series. And if you have taken probability, you can rewrite this in a different way. This is the sum from n equals to 0 to infinity, and then this is n choose k, actually the other way around, k choose n. So this and this is exactly the same thing, so you can write it either way. That's a very common thing in probability, and then this will be x to the n. So this can, once you have this, you can use it to find the Taylor's expansion of anything that looks like this. Remember, this is for the function f of x 1 plus x to the k, where k actually doesn't even have to be a whole number. Now, for the point of the class, or the purpose of the class, it actually makes it easy to expand this from the very beginning. So this is equals to 1 plus kx plus k minus 1 x squared over 2 factorial, then k minus 1 k minus 2 x cubed over 3 factorial, and so forth. So this is actually easier to use. For example, let's say you wanted to expand this. Again, you can do this by brute force, the way we did the previous two examples, and that's fine, but it can take you a while. Otherwise, you can use the binomial series. All you have to notice is that this is the same thing as 1 plus x to the 1/3. So therefore, here, the value for k is 1/3. So if we use the formula, it will be 1 plus 1/3 x. It will be 1/3, and 1/3 minus 1, it will be minus 2/3 x squared over 2 factorial, and so forth. This will be 1/3 times minus 2/3 times minus 5/3 x cubed divided by 3 factorial, and so forth. So it's not that bad, but you should use this to expand. And that's it.